Here you go.
Okay, so good morning, everyone. So I'm going to continue a little bit on this theorem of resolution of vector fields in dimension 2. So I recall you that we had this construction where I essentially explained it to you how to choose the local strategy of blowing up based on the Newton polygon, right? So I recall for you this picture here where in fact once we suppose that you have this an important point which lies on the divisor, you have this main vertex, which in some sense will provide you the invariant for the resolution, because the idea is to decrease the height of this main vertex by blowing up with a weight which is determined by the slope of this edge, which is adjacent to the main vertex, right? So, of course, well, I've showed you that once this main vertex attains its lowest position, either 0 or -1, then we get an elementary situation. Okay, so this is the invariant, this H. Just a quick recall here. So I showed you that this invariant, in fact, is doesn't depend on the choice of local coordinates, as long as you impose that our coordinates are adapted to the divisor. And then I showed you that this naive choice of coordinates usually don't give you an improvement by blowing up because of this phenomena of complete compensation, right? So the idea is that if the initial form that you get by restricting, let's say, the support of the expansion to this main edge, if it's given by a sort of a complete linear form, complete quasi-homogeneous form, then by this blowing up, which corresponds, as I said, to a combinatorial transformation on the Newton polygon, but followed on the last step by such sliding, let's say, the translation, which allows you to consider each point on the divisor is let's say it acts in a non-combinatorial way on the coefficients of your derivation, and so you have to control the fact that you can have a complete compensation here, right? So I extended to I showed you an example where this in this last phase, which I call the sliding phase, you can in fact obtain a height which is does not decrease. Okay, so it cannot increase either, but you can have no improvement if you don't pay attention to such kind of example, right? So this was the example. We're going to go a little bit quick on this. So the idea to fix this problem is to consider a way to stabilize the main edge. So I recall that this is precisely in some sense, this is the only situation where this problematic behavior can appear, where you have a sort of initial form which is complete here, right? And in fact, at the end, by transformation, you get this term, which will becomes y by translation, right? So to prevent this, I introduced this concept of edge stable. So the idea is that once you have this, let's say you choose an adapted system of coordinates, you try to test all such kind of polynomial change of coordinate to see if you can eliminate all points on the edge except the main vertex, right? So you test this map, and you say that the edge, the Newton polygon is edge stable if you're not able to eliminate all the main edge by any map of this file. So, right. Okay, so the local resolution say that once we start with an edge stable situation, then the height will improve. So the idea is that once you get, now I'm going to show that in fact you can always stabilize the edge. right? So, but what I have proved last time says that once you get a stable situation, then in fact the environment improves if you apply this local strategy, which consists of blowing up with the weight, or more precisely with the filtration determined by the weight associated to the slope of the edge E, right? Okay, so I'm not going to go back to this reasoning here, but I'm showing you that essentially there is these two cases, and okay, yeah. So now I'm going to just to say what remains to prove, just to complete the proof, is that in fact it's possible to find an edge stable situation, right? So this the procedure that I call the edge stabilization. In fact, this is also a point which will be quite important when I explain to you how to generalize this to the higher dimension, at least in dimension 3. So there are two claims here. The first claim that once there always exists an adapted system of coordinates, x and y, such that the Newton polygon computed with respect to these coordinates will be edge stable. And in fact, there is a second part which says that in fact the filtration, which is determined by these coordinates x and y, and the slope of the edge is unique, in the sense that if you have two different coordinates in which the Newton polygon is edge stable, then the filtration, or more, yes, the local algorithm which is prescribed by these two coordinates, or more precisely the filtration of the local ring, which is determined by the weights of the main edges of with respect to the two coordinates coincide. Okay, so the second statement says, more precisely, that the filtration, or more the filtration is something which is intrinsically determined by delta and the divisor. So it doesn't depend on the choice of coordinates, as long as you choose a coordinate which is stable. So this is one of the reasons why I don't know if you remember that I said to you that if you work on the category of orbifolds, at each time you have to be careful with the fact that all the objects that you are going to use will be G invariant, where G is the group of symmetries, right? So it's not very clear that the weight that we choose will be G invariant. But now with this statement, it's clear that if the vector field has some symmetry, this symmetry, so it's since the filtration is intrinsically determined by the derivation, this symmetry will also be inherited by the filtration, right? So the filtration will also be G invariant, and in this way we can make a blow up with let's say which will respect the G action and the group action and get something which is a new orbifold by blowing up. Okay, so there are two parts here. So the first part is a very let's say easy argument. How do you get this stabilization procedure? So we start with any adapted coordinate system, let's say x, y, 0, and then we proceed simply as following. So there's let's say an iterative algorithm. If by chance we have an edge stable situation, then we stop. Otherwise, as I said, if it's this x, y, 0 is edge unstable, then by definition there exists a polynomial change of coordinates of this type. Let's say y1 equals to y0 plus psi 0 times x to k0, where k0 is just the slope, which eliminates all along the main edge E0, right? So now you pass to these new coordinates x, y1, and you start again, right? So I claim that this procedure eventually stops and you attain a edge stable situation. Why? Because, so let's reason by contradiction. So we suppose that is not the case, and then you remark that you get an infinite sequence of coordinate changes where each one corresponds to, let's say, to the elimination of the edge which is unstable in the preceding step, right? So you have this sequence of coordinate changes where at each time you have a slope ki, which is beta I over alpha y. And the important thing is that this sequence of positive integers ki is strictly increasing, right? So this is why, because, well, you see that you easily see that each time that you eliminate an edge, you get some edge which is a little greater slope, and then you continue, right? So of course, this always varies in a discrete. Well, these are integers, but so in fact, this sequence of change of coordinates, they converge. When you compose all of them, they converge to a formal change of coordinates of the type y infinity. Let's say it's equals to y0 plus this formal series psi I x to the power ki, right? But now, when you look at the Newton polygon in the new form, the formal coordinates given by x and y infinity, you have this thing, right? So at infinity, since at each time the slope increases by let's say by a discrete amount, then at the end you have the Newton polygon should have this, let's say the main edge should be an horizontal edge at the height of the point M. But I recall that this situation corresponds precisely to the fact that the locus given by y infinity equals to 0 lies on the nilpotent locus of M, right? But this is a contradiction because, well, already, because I suppose that the nilpotent locus is of codimension 2, but moreover, yes. So yeah, okay. So it's an analytic set of codimension 2, and so it cannot have a component of codimension 1 either in the formal completion. Okay, so this contradiction says that this refinement procedure should stop at some point, and you attain a stable situation, edge stable situation. Okay, so now let's show that you have the uniqueness of the filtration. Okay, so it's more or less the same type of argument. Suppose that you have two different coordinates called x, y, and x prime, y prime, which are both give an edge stable Newton polygon, right? So now you can consider the change of coordinates which maps x, y to the x prime, y prime. Since I recall it should preserve the divisor. It should be of this form, right? But now I claim that this map should preserve the filtration given by the weights of the main edge. So let's suppose again by contradiction that this is not the case. But first of all, how do you characterize the fact that this chain of coordinates preserves the filtration? It's very simple. You just expand G as G0 of X times Y, some capital G of X and Y. And then to say that this change of coordinates preserves the filtration amounts just to say that G0 should be of order X of B over alpha, right? So I've just illustrated this in this upper drawing here. So you see that this dashed arrow here corresponds to a chain of coordinates which doesn't preserve the filtration of determined by the leftmost Newton polygon, but when you the two other edges here, which are solid arrows, correspond to maps which preserve the filtration, right? So now let's suppose by contradiction that the G0 does not satisfy this condition, right? So now you look at the small order terms, non-zero, let's say non-zero order term of in the expansion of G0. and it it gives you let's say some term of the form x to the power k, with k smaller, strictly smaller than b over alpha, right? So now I consider with some coefficient at n. So now I just consider the polynomial chain of coordinates associated to this first initial non-zero term of G0, right? So this will be of this form here. And now I consider the Newton polygon on the coordinates x and y1, right? So in some sense, I can consider this change of coordinates from xy to xy1 as an intermediate step between xy and x prime y prime. Right? I can factor out this first change of coordinates, and then there is a second change of coordinates which maps y1 to y prime. Okay. So of course, now we look at the edge of the Newton polygon associated to delta in the coordinates x and y1. So it has an edge of slope k, which is strictly smaller than beta over alpha. Why? Because in fact, well, this is a very simple computation. When you, so this corresponds to an sliding along this dashed arrow that I've shown to you here. So when you make a change of coordinates corresponding to yes, to, let's say, to x plus xi x, sorry, y goes to y plus xi times x to the power k, it will necessarily create an edge of slope k, because, well, I can say this in a more precise way by stating that the action of this chain of coordinates on the Newton polygon is effective in the sense that it will necessarily create something on the support which lies along the slope k here. Okay. So you create this new edge of slope k, strictly smaller than b over alpha. Okay. But now, by hypothesis, this Newton, the Newton polygon of delta with respect to x and y1 should be edge stable. Why? Because I recall, so just go back a little bit. I recall that I extract this psi times x to the power k is just the initial part of the Taylor expansion of G0, right? So in fact, this is precisely the part which corresponds to the edge of the Newton polygon in the x prime y prime coordinates. Okay, so I repeat, I say that the 1k initial part of delta with respect to the variables x, y1 is precisely the same thing as the e prime initial part of delta with respect to the coordinates x prime, y prime. Okay, just because I'm extracting the initial part by going from xy to xy1. Okay, so by hypothesis, there is edge stability on the coordinates x, y prime, and so the same should be true for the coordinates x, y1. Okay, but of course this could not be edge stable because the inverse transformation, the ones which goes from y1 to x to y, is precisely the transformation which eliminates this edge of slope k, right? So I just claiming that if you go back, you have created an edge along this dashed line, but it's, of course, it cannot be edge stable because you can eliminate it by just applying the inverse transformation. Okay. So by this very simple argument, we show that all edge stable situations determine the same filtration of the the same filtration of the local ring. Okay. Well, I do you have some question? Anyone has any question about this? Okay, so
excuse me, Daniel.
yes.
You said before that the KI, when you have proved the existence, the KI was were integer numbers.
Yes.
Why integers? Usually where they are. No, after this, they are given by beta I over alpha I.
Okay, so I assume that you have edge. So I am in this second situation, right? So I assume that the edge is unstable. Okay, so by which I mean that I can eliminate all terms in the main edge by a change of coordinates of this type. Okay, but in this definition, it's implicitly implicitly assume that this should be an integer number. Okay.
Okay.
Because I recall too that in the case where so in the proof of the theorem, there is these two separate situations where beta over alpha is an integer.
Okay.
This is the case where you can have this compensation phenomena, which is problematic. But in the case where it's not an integer, then there can be no compensation phenomena. So in this case, I'm automatically, if b over alpha is not an integer, then it's automatically edge stable. Okay.
Yes, right.
Because in this case, you cannot have this bad compensation phenomena that I explained to you.
Okay. Okay. Yes.
Because of the symmetry, there can be no root of a very large maximal multiplicity because of the fact that the root should be on the cyclic permutation order. Yeah. Okay. Okay. So some general remarks. So I think I can use this two-dimensional situation to illustrate some interesting phenomena, which shows that it's somehow more difficult to desingularize vector fields than to desingularize, let's say, a function or ideal shifts. So, for instance, one of the basic tools that you use to, let's say, that is used in the Hironaka's theorem and also in the more modern approaches, is the so-called maximal contact argument, which allows you to proceed by induction in the dimension. So I'm going to explain this very quickly in this case and try to convince you that you cannot have maximal contact, at least in such a naive way, in the case of vector fields, right? So I claim that essentially the maximal contact situation is what you obtain by what people call the Chinhausen preparation. Okay, so I recall very briefly what is this. This is all about. So suppose that you have a singular hypersurface in let's say, any dimensional ambient space, which is, let's say, so a germ of, let's say, of singular hypersurface, which is given by generated by the zero of such a function f like this. So up to a generic exchange of coordinates, I can suppose that it's of multiplicity h, and you have some initial monomial of this type, y to the power h, and then some, let's say, some polynomial on y with coefficients on the other coordinates x, ai. Okay. So the idea of the Chinhausen preparation is to eliminate the terms on y to the power h minus 1. So this is very easily attainable by just making this change of coordinates here. Okay, so I think, I don't know, Chinhausen, I think, dates back to the 17th century. He used this to solve the polynomial equations. Okay? But in our case, this corresponds geometrically to a very simple observation that if you draw the Newton polygon of the function f, you are trying to eliminate all the support which is contained on the hyperplane at height h minus 1, right? So eliminating the term on y to the power h minus 1 means that you cannot have any let's say, any point of the support on this dashed hyperplane. Okay. Well, what does it imply? It implies that if you try to compute the locus of a multiplicity h of f, so the multiplicity h locus of f can be seen as the locus where all derivatives of all partial derivatives of f with respect to the variables up to order h minus 1 are 0. So in particular, this is the locus where this derivative vanishes, right? But if you derivate the expression of f h times with respect to y, you see that you just get y times h factorial. Sorry, I forgot h factorial here, because precisely because we eliminate the terms on y minus 1. So this locus is contained necessarily in the hypersurface y equals to 0. So this is the so-called maximal contact surface, because in fact, once you get the situation, each time you take a blowing up with center contained on the h multiplicity locus, the situation remains stable in the sense that the locus, if the strict transform of f has a locus of multiplicity h, it will be contained on the strict transform of the hypersurface h. Okay. So this is a very nice situation, which in fact allows now you to work with the so-called ideal of coefficients in a n-1 so in fact you reduce the dimension by looking at only to what happens by restriction to the surface h, roughly speaking. Okay, so let me try to do the same thing for vector fields, and I'm going to show to you that even in dimension 2 it gets quite tricky. Okay, so let's suppose that you have this analogous situation where you have this y to the power h, which corresponds to the height of the main vertex, and then I suppose that you have some sort of expansion like this, right? So now, what should be the analogous of this differential operator action here, right? So we are trying to determine the multiplicity h locus. Well, it's quite okay. So it's in the most naive way, you say that this is a partial, let's say a derivation which acts on f, and then you iterate this operation h minus 1 time. So the natural, let's say, the natural way to do this for a derivation is just to apply the derivation over with respect to y on the derivation, but in this case, the Lie derivative corresponds just to applying the Lie bracket h times. Okay, so you apply the h derivative as a Lie bracket h times to your initial vector field or initial derivation. So this I commented to you yesterday that this is the adjoint operator. So then you get a new derivation. So each time you decrease the power of h of y, which appears here. So after h steps, you get something like this. So there's an initial form. Yeah, so there is an initial form like this. And then there are higher terms, which I don't want you to comment on, which comes from perhaps from this part here. But what should be the analogous of the maximal contact surface, right? So here, what I'm looking for is an invariant curve for this new derivation, delta, which should be of the form of a graph y equals to some f of x. Okay. So what I mean by invariant, it means that if you apply delta as a derivation to x minus f, it should give a function which lies on the ideal generated by x minus f. Okay, so if you write this, in fact, it gives you a differential equation on f, as I'm going to show to you in a moment. Right. So under which conditions can we find an invariant surface for this, for let's say for a vector field which has an initial form like this? So let me give you an example to show that things are not very simple. So by later you can cook up an example where delta, which appears here, has the following form. Okay, so x squared d over dx minus y minus x d over dy. Okay, so you see here this term on y, which I colored in blue, gives you the monomial, which is so I'm drawing here in this picture. I'm drawing the monomials which are associated to this, right? So so there are three monomials. The red one is 1, 0. 0, 0 is just the blue one here, corresponds to y d over dy. And there is the orange one, which is a point which has negative first coordinate. Okay. So let's say the Chinhausen transformation that I would like to do corresponds precisely to try to eliminate all the monomials which are at height h minus 1, or in this case, it means try to eliminate this orange vertex here, right? So we try to eliminate this by, let's say, by making this change of coordinates. Y goes to y minus x, right? So this is precisely the way to try to make this y minus x becomes just a y. But once you do this, you have to recall that there is a contribution that comes from the red vertex, which in fact gives you this new expression here. Okay. So in fact, what I'm just drawing here the arrow by meaning that the x squared d over dx term now gives you a contribution which is which has let's say which gives you a vertex of coordinates 2, minus 1. Okay. Now you iterate, so you try now to eliminate this new terms, the new term y minus x squared by making y goes to y minus x squared, but then you get 2 y minus 2x cubed, right? So it's even more to the right, to the right here, and then you continue, and now you get 3x to the 4. Okay, of course you can imagine that this will not end, because at each time this term on x squared will give a contribution, and at the end you get what we call at the curve limit, you get the equation of this invariant curve, which is precisely given by this expression. So I think some of you know this is what is the so-called the center manifold of the Euler's equation, right? So this should play the role of the maximal contact surface, at least if you try to interpret this procedure in a, let's say, more or less naive way. But unfortunately, as you see, there is this very large, fastly growing coefficient, which shows that this series has a 0 radius of convergence. So it's not analytic. So in some sense, the maximal contact surface for a vector field can be a non-analytic object. So in this case, I've drawn this. This is the phase portrait of the Euler surface. So in this case, the maximal contact surface is formal, a non-convergent curve, and but it's C infinity. Okay. In fact, well, I think you can prove that it lies on a O minimal structure, which is the Pfaff enclosure of the R analytic. Well, I think you don't even need the analytic functions here, because you see the coefficients of your vector field are just polynomials.
Oh, Daniel, sorry.
Yes.
Can you hear me? Yeah. So when you say there is a C infinity curve, so is there a specific C infinity curve which plays the roles of the center manifold here? Is it what you mean?
No. I mean, if you try to let's say to find this curve, it should be a curve which is invariant by should be invariant by this delta, but the unique choice is dictated by this algorithm. So you end up with the unique possibility for this curve, which is given by
yeah, that's clear. But afterwards, you mentioned a C infinity curve, which should
yes, because each one of these, you see here, I have drawn the phase portrait of the Euler's equation, So I know if perhaps most of you know this. So there is all these curves which are on the right of the on the positive x-axis, on the positive side of the x-axis, they have a flat contact with the at the origin of the type exponential of -1/x. Okay, so in fact, if you try to find, each one of these curves here is a center manifold on the
that was my question. So there is not one specific curve which plays a role of center manifold. Okay.
Yeah. You cannot differentiate. Each one of these invariant curves is a center manifold.
Okay, thank you.
But yes, so but these curves are all lie in this if I'm not wrong, I think they lie on a minimal structure. Okay, and so now I just finished this part of on two-dimensional vector field. So I just summarize what I would like to do next, and then give you an example of a phenomena, a very strange phenomena, which can appear in dimension 3. Okay, so what do I intend to do in the next lectures that remain? So first of all, explain to you how to generalize these ideas in the case to the case of foliations in dimension 3. Okay? So in fact, in dimension 3, there are, let's say, the proof is more complicated, but the essential ideals are the ones that I explained to you. It's just a little bit more technical. I will not be able to provide you the full details, but it's, let's say, conceptually is not much different from what I explained to you. So the second thing is what to do with the final models in dimension 3. Because, well, there is a very well-developed theory for, let's say, for these elementary singularities in dimension 2, and it's much less understood in dimension 3 and greater. Okay, so there is a lot of work to be done here, and I'm going to show you some examples which, in fact, prove, let's say, that perhaps it's not, even when you attain this elementary situation, it's not enough to do a good theory of normal forms. Okay, so in fact, you can continue to do more blowing ups to improve this situation, even when you attain the elementary case. And then finally, I'd like to explain to you. Yes, I'm just looking for that. A particular case of this three-dimensional problem where, in fact, you just study the 2+1 problem. So what is the 2+1 problem? Is the case where you have, so it's a foliation dimension of 3, but in fact, it's given by a family of planar analytic foliations. So foliations in surface, let's say in domains of R2, which depends analytically on one parameter. Okay, so this is what I call this 2+1 case. Well, in this case, I think that there are, let's say, some goals which, from my modest perspective, are more or less attainable in a short term. So first of all, give a full catalog of cases, okay, of one case, study the normal forms which appear, and then provide the finite cyclicity, prove the finite cyclicity conjecture for this one parameter families, right? So in some sense, this will give you a proof of the Hilbert's 16 problem, at least the finiteness part, in the case of analytic families depending on one parameter. And then, well, if I hope to talk to you about the case of dimension greater or equal than 4. So, yes. So in this case, there are new ideas which are needed. It's in fact, it's not. It's I think something which is a work in progress, because the ideas that I explained to you now, which work in dimension 3, doesn't apply directly to dimension 4 because of I'm going to show to you some essential issues which doesn't allow us to extend this to higher dimensions. And now I would like to propose to you a new approach, which is based on something which is called the Kemp instability theory. And here there is a very strong analogy with something which appears on geometric invariant theory. well, I don't know if I have 1 minute more. I'd like just to give you a very, in 1 minute, one example of an interesting phenomenon which can appear in vector fields in dimension 3. Okay, so it's quite strange. So center manifolds are not necessarily C infinity. Okay, so I knew this example from a paper of Sebastian van Stream on 79, and when I explained this example to Michael McQuillan. He already knew this and said to me that, well, this is called the monster, right? So it also appears, he discovered this example independently in his work. So it's given by this expression here. Okay, so this is a three-dimensional vector field. Yes, I just need 2 minutes more. Yes, so it's a three-dimensional vector field. And you see that here that there is a non-zero eigenvalue in the z direction, because you have this expression here, z d over dz, right? So now what I want to do is to try to find an invariant surface, which is called the center manifold, of the form z equals to a graph, let's say z equals to f of x and y. Okay. Well, when I try to find an invariant surface, I recall to you, yeah, so I'm just writing the equation that delta applied to z minus f should be on the ideal generated by z minus f. And this gives you a partial differential equation of this type. Okay, sorry, this doesn't appear well, but this is 1 minus xy times d over dy multiplied by f equals to this expression here, right? So this is a partial differential equation for f. And now I suppose that f is C infinity, and I try to expand this in terms of the y variable with coefficients which depend on x, with a C infinity functions on x, right? So when you take this equation and you plug in the expansion, in this partial differential equation, you get that ak should necessarily be given by this. Okay, there's no choice. And then it means that you see here that AK is not defined if K is if X is equal to 1 over K. Okay, so it means that if X is of the form 1 over K, you cannot obtain this expansion for K greater than 1 over X. In other words, that the center manifold is CK, is not CK for K for X smaller than 1 over K. Right. So I can show to you. Well, I'm going to finish now. So this means if you take the slice is given by X equals to 1 over K, what you get in this slice is that the center manifold should be the equation of something of the form y equals to x to the power k times log of x.
Daniel, sorry to interrupt. No rush. You have till noon in Toronto time.
Ah, it's, okay, sorry. Yes, more 5 more minutes, right?
So please don't rush.
Sorry, I thought that I had to finish. And yes, sorry. So I go to be more slow. So so this is the so-called monster. Why? Because you see that this slice is given by x equals to constant, gives you the expression of the intersection of the center manifold with the plane x constant equals to constant, right? So in this slice here, you have something which is of differentiability c at most c k minus 1 because of this expression here, right? So they are right. So if you derivate k times, you get log here. So if you approach 0, of course, the order of differentiability increases, but on each neighborhood of the origin, you get something which is not of class C infinity, right? So if I recall well, Jean-Philippe Rollin once asked me about this example because he was trying to show the existence of a non-minimal structure. It hasn't a C-infinity cell decomposition. So, but I think that at the end he used another type of example. But in this case, if there is a non-minimal structure which contains this center manifold, this computation shows that this cannot have a C-infinity cell decomposition. Okay. So this is, of course, is let's say quite simple situation that you can obtain in dimension of 3, and it's, let's say, it's quite surprising, but in some sense, it shows you that there are new phenomena which, let's say, which should, I think, deserves to be studied when you look at these final models. Yeah, okay. I think I have another example to show to you, but I don't know if I have five more minutes. But do you have any question about this example? Perhaps.
Yes, I have. It is known or that there is a center manifold for this example or something like that, which is minimal.
No, I don't think so. Yes, as I said to you, I think that people don't know if this center manifold belongs to a non-minimal structure because it's not. You see, it's not a Pfaffian set. It's not given by the leaf of some foliation. It's a union of
even for this example where you put there that something well it was y equivalent to x to the power k logarithmic. It's not exactly the logarithmic.
No,
okay.
Yeah, okay. So, in fact,
no, I was
in fact,
I was confused by your expression. I thought it was really the logarithmic that solves the question.
Yeah, what happens here is that if you let's say if we restrict your vector field to the slice given by x equals to 1 over k, then you can show that there is a system, let's say an analytic change of coordinates, which conjugates locally at this, let's say at this black point, this vector field to the vector field with a resonant node. For those of you which know this, okay. So there is a resonant node here, and there is, let's say, one invariant curve of this resonant node which is tangent to the horizontal axis. And it has this expression here, okay. But yeah, so the problem is that
this curve may be Pfaffian, no?
Yeah, yeah, it's Pfaffian, yes, but
yeah. Anyhow,
yeah. So the restriction of this the center manifold to each slice is a Pfaffian curve. This is for sure. Okay.
Yeah.
But
yeah, but it doesn't mean anything for a moment.
Yeah, but I don't know if you can say that there is some sort of Pfaffian family structure here, because you see that it's Pfaffian on each slice, but now you want to take all slices all together. So as far as I know, this is an open problem to show that, let's say, in this very natural example, you get something which lies on a minimal structure. And in this case, in some sense, you would get a quite natural example of a non-minimal structure which doesn't have a C-infinite cell decomposition.
Okay.
But well, I had another example, but perhaps I go to talk to you this in the next time, which concerns the singular perturbation situation. But I just showed, I'm going to explain this to you next time. So thank you very much for your attention.
Thank you. I'll stop there.
Thank you.